The thermometer outside read 42 below zero. Inside Jacob Whitmore's underground shelter, it was a comfortable 55 degrees. Oh, and he hadn't lit a fire in 3 days. While other trappers huddled around roaring flames, burning through cords of firewood just to stay alive, Jacob sat in his earth-sheltered dugout, warm and comfortable, reading by candlelight. The other mountain men thought he was crazy when he started digging into the hillside back in the summer of 1836. They called it a grave, a hole for a living man. They said he'd drown when the snow melted, suffocate from bad air, or collapse the whole thing on his head. But Jacob understood something they didn't, something the native peoples had known for thousands of years, something our ancestors understood but we've completely forgotten. The earth itself is a battery of warmth, a thermal mass that holds steady at around 50 to 55 degrees year-round, just a few feet below the surface. While the air temperature might swing from 90 degrees in summer to 40 below in winter, a 130-degree range, the ground stays constant. And if you knew how to tap into that stability, if you understood how to engineer a structure that worked with the earth instead of fighting against it, you could survive a Rocky Mountain winter with a fraction of the firewood, a fraction of the effort, and 10 times the comfort of any surface cabin. Jacob Whitmore's underground heat trap wasn't just a hole in the ground. It was a sophisticated piece of thermal engineering, built with nothing but hand tools, local materials, and deep understanding of how heat moves through soil, air, and stone. This is the story of how mountain men engineered underground shelters that turned the earth itself into a heating system, and why that knowledge matters more now than ever. Jacob Whitmore arrived in the Wind River Range in the spring of 1835. He was 28 years old, originally from Pennsylvania, and he'd spent 2 years trapping in the lower elevations of the Rockies before pushing deeper into the high country. He was quieter than most mountain men, more thoughtful, the kind of man who watched and learned before acting. His first winter in the Wind River Range nearly killed him. He'd built a standard log cabin, single-wall construction, chinked with moss and mud, stone fireplace at one end. It was identical to every other trapper's cabin in the territory. And like every other cabin, it was a miserable place to spend a winter. The logs provided some insulation, maybe an R value of 8 to 10 at best. For context, modern building codes require R values of 30 to 40 for walls in cold climates. Jacob's cabin was losing heat almost as fast as his fireplace could produce it. He burned through 4 cords of firewood a month, exhausting himself with the constant work of cutting, splitting, and hauling logs. And still, the cabin stayed cold. Frost formed on the inside walls. His water bucket froze solid 3 feet from the fire. On the coldest nights, he'd wake up with ice in his beard, and his breath forming clouds thick enough to obscure his vision. But what frustrated Jacob most wasn't the cold itself. It was the inefficiency. He'd been trained as a millwright before heading west, and he had an engineer's mind. He could see that he was fighting a losing battle. No matter how much wood he burned, no matter how carefully he chinked the gaps, the fundamental problem remained. His cabin was a box sitting on top of frozen ground, surrounded by air that could drop to 50 below zero. Every surface was losing heat. The walls radiated warmth to the outside air. The roof conducted heat upward into the sky. The floor drained warmth down into the frozen earth. He was trying to maintain a 70-degree temperature inside while the outside temperature was negative 50, a 120-degree differential. And his only weapon was a single fireplace burning wood that he had to cut with a handsaw and an axe. There had to be a better way. The answer came from an unexpected source. In the spring of 1836, a Shoshone woman named Falls, at dawn, came to trade at Jacob's cabin. Her husband was a French-Canadian trapper named Michel Beaumont, and they spent winters in the mountains rather than returning to lower elevations like most trappers. Jacob asked her how they survived. Where was their cabin? Falls at dawn smiled and told him they didn't live in a cabin. They lived in the earth. She described their winter shelter, a structure dug into a south-facing hillside, with a roof of logs and sod barely visible from the outside. The walls were earth, packed hard and smooth. The floor was earth, covered with layers of hides and woven mats. A small fire pit in the center, with a smoke hole that could be adjusted or closed depending on need. And the temperature inside, she said, never dropped below comfortable, even on the coldest nights. Even when they let the fire go out completely. Jacob was skeptical. He'd seen root cellars and knew they stayed cool in summer, but he'd never considered that the same principle might work for warmth in winter. Falls at Dawn explained it simply. The earth remembers summer, she said. Deep down, it holds the warmth of summer sun. Sky changes, very cold, very hot. Earth changes slow. You go into the earth, you find the earth's temperature, not the sky's temperature. This was the key insight that would transform Jacob's understanding of shelter. The ground, even in the mountains, maintains a relatively stable temperature year-round. This temperature, called the ground temperature or earth temperature, varies by location, but in most of the Rocky Mountain region, it stabilizes around 50 to 55 degrees Fahrenheit at a depth of about 6 to 8 feet. This happens because the earth is a massive thermal mass. During summer, it slowly absorbs heat from the sun. During winter, it slowly releases that heat. But the changes happen so gradually, and the volume of Earth is so large that the temperature at depth barely fluctuates. It's a natural battery, storing and releasing energy over the course of the seasons. For a person trying to survive winter, this 55-degree Earth temperature is a gift. If the outside air is 40 below zero, and you can create a space where the walls are 55 degrees, you've instantly created a 95-degree differential in your favor. You're no longer fighting to maintain a 120-degree temperature difference. You're only fighting to maintain a 15 to 20-degree difference. And that changes everything. Jacob spent the summer of 1836 planning and building his underground shelter. He chose a south-facing hillside on his trap line, steep enough to allow for good drainage, but not so steep that it would be unstable. The south-facing orientation was critical. It would allow winter sun to reach the entrance and provide passive solar heating. The hillside location meant he could dig horizontally into the slope rather than straight down, making construction easier and providing natural drainage. He started by excavating. Using a pick, a shovel, and a pry bar, he dug into the hillside. The first few feet were difficult, cutting through root systems and rocky soil. But once he got past the surface layer, the digging became easier. The soil in that particular hillside was a dense clay loam, stable and workable. He dug a tunnel approximately 6 feet wide, 7 feet high, and 16 feet deep into the hill. This created a rectangular space, roughly 10 feet by 16 feet, the size of a modest room. The entire excavation took him 6 weeks, working alone. That's over 200 hours of digging with hand tools, 200 hours of hauling soil and rock out of the tunnel in buckets. It was brutal, exhausting work. But Jacob understood that this was an investment. Those 6 weeks of hard labor would pay dividends for years. Once the main chamber was excavated, Jacob began the careful work of shaping and stabilizing the space. The walls were carved as smooth as possible and then packed hard using a wooden tamper. This compaction was critical. Loose soil would eventually crumble and collapse. Compacted soil would hold its shape for decades. He carved a shallow drainage channel along the base of each wall, leading to a sump pit at the back corner of the chamber. This would collect any water that seeped through the walls and prevent the floor from becoming muddy. The floor itself was excavated an additional 6 inches and filled with layers of material. First, a layer of fist-sized stones for drainage, then a layer of gravel, then a layer of sand, finally a surface layer of smaller, flat stones fitted together like a crude mosaic. This created a dry, stable floor that would remain comfortable to walk on and would reflect heat rather than absorb it like bare earth. The entrance was the most complex part of the design. Jacob built it as a tunnel, not a simple doorway. The entrance tunnel extended 8 feet from the main chamber, sloping slightly upward toward the outside. This created a cold trap. Cold air, being denser than warm air, would sink down and pool in the entrance tunnel rather than flowing into the main chamber. Warm air in the main chamber would rise and stay trapped inside. This simple physics trick meant that even with the door open, the main chamber would retain most of its warmth. The entrance tunnel also served as an airlock, providing a space to store firewood, tools, and wet clothing. It kept wind from blowing directly into the living space, and it provided a psychological buffer, a transition zone between the harsh exterior world and the warm, secure interior. The door itself was built from thick planks of pine, fitted into a frame that was set into the earth walls of the tunnel. It opened outward, which was critical. If snow drifted against the door, he could still push it open from inside. An inward opening door could trap him inside if heavy snow piled up. The door was hung on iron hinges that Jacob had packed in from a trading post over 100 miles away. He sealed the gaps around the door frame with a mixture of clay and buffalo hair, creating an airtight seal when the door was closed. He also built a smaller inner door at the point where the entrance tunnel met the main chamber. This second door created a true airlock. When coming or going, he could open one door while keeping the other closed, minimizing heat loss. The roof structure was where Jacob's millwright training showed most clearly. He couldn't simply pile earth on top of logs and hope for the best. Earth is heavy, approximately 100 pounds per cubic foot when dry, and up to 120 pounds per cubic foot when moist. A roof covered with 3 feet of earth would need to support several tons of weight. He started by placing heavy support posts inside the chamber. These were cottonwood logs, approximately 12 inches in diameter, set into holes dug 2 feet into the floor. He used 4 posts, creating 2 rows that ran down the length of the chamber. These posts supported a ridge beam, a massive log that ran the full 16-foot length of the chamber. From the ridge beam, he laid rafters, logs approximately 8 inches in diameter, spaced every 18 inches. The rafters extended from the ridge beam to the walls, where they were set into notches he'd carved in the earth walls. This created a peaked roof structure inside the excavation. On top of the rafters, Jacob laid a deck of smaller poles, placed perpendicular to the rafters, and spaced about 4 inches apart. On top of these poles, he laid a layer of bark, stripped from cottonwood trees. The bark served as a barrier to prevent the next layer from sifting down through the gaps. On top of the bark, he placed a layer of prairie grass and small twigs, about 6 inches thick. This layer would act as insulation, trapping air and slowing heat transfer. On top of the grass layer, he spread a thick layer of clay, approximately 3 inches thick, which he'd mixed with water and chopped grass to prevent cracking. This clay layer served as a moisture barrier. Finally, on top of everything, he piled earth, 3 feet of earth, creating a massive thermal mass above the living space. This earth layer would absorb heat from inside during the day and release it slowly during the night. It would also provide tremendous insulation, with an R value estimated at around 40 to 50, far exceeding the insulation value of any log cabin wall. The ventilation system was perhaps the most ingenious part of Jacob's design. He understood that he needed fresh air, but he also needed to minimize heat loss. His solution was elegant. He built 2 ventilation shafts. The first shaft was for air intake. This was a clay pipe, approximately 4 inches in diameter, that ran from the outside down through the earth roof and into the chamber. The intake point outside was positioned low on the hillside, just a few feet above the entrance. The pipe ran down through the earth, entering the chamber near the floor. As outside air entered through this pipe, it was warmed by contact with the earth surrounding the pipe. By the time it entered the living space, air that might have been 40 below outside had been pre-warmed to around 40 or 45 degrees by its journey through the earth. This was passive heat recovery. using the thermal mass of the earth to condition incoming air. The second shaft was for exhaust. This pipe ran from near the ceiling of the chamber up through the earth roof, extending about 2 feet above the surface. This created a natural draft. Warm air inside the chamber would rise and exit through the exhaust pipe. This created negative pressure in the chamber, which pulled fresh air in through the intake pipe. The system was self-regulating. The warmer the interior, the stronger the draft. On extremely cold days, Jacob could partially block the intake pipe with a wooden plug, reducing the air exchange rate and conserving heat. On warmer days or when cooking created smoke, he could open the intake fully and allow maximum ventilation. For cooking and additional heating, Jacob built a small firebox in one corner of the chamber. This was a box made from stacked stones, about 2 feet square and 2 feet high. The firebox had its own dedicated chimney, a clay pipe that ran up through the earth roof. The firebox design was crucial. Jacob built it with a baffle system that forced smoke and hot gases to take a circuitous path before exiting. The smoke would enter the firebox, then travel through a horizontal section inside a stone channel that ran along the base of one wall, then turn and travel back along the base of another wall before finally entering the vertical chimney pipe. This meant the smoke traveled approximately 30 feet before exiting the shelter. During this journey, the hot smoke transferred much of its heat to the stones of the firebox and the surrounding earth. Very little heat was wasted up the chimney. A small fire, burning for just an hour or two, could keep the chamber comfortable for 12 hours or more. The stones would absorb the heat and release it slowly. The earth walls and ceiling would absorb heat and release it slowly. The entire structure became a thermal battery. If you're finding this information valuable and want to learn more forgotten survival skills from the past, hit that subscribe button. New videos on traditional wilderness knowledge drop every week. You won't want to miss what our ancestors knew that we've forgotten. Jacob moved into his underground shelter in late October of 1836. The first test came in November when an early blizzard hit the Wind River Range. The temperature dropped to 35 below zero. Wind gusted to 50 miles per hour. Snow fell for 3 days straight. Above ground, the storm was catastrophic. The wind tore at anything exposed. The cold penetrated every gap, every crack in conventional shelters. Trappers in standard log cabins burned through their firewood stores at alarming rates and still shivered. Jacob, in his earth shelter, barely noticed the storm. The wind roared above, but underground, the air was still. The temperature outside plummeted, but inside the earth walls stayed at 55 degrees. Jacob lit a small fire in his firebox for about 2 hours in the evening, just enough to bring the interior temperature up to 65 degrees or so. Then he let the fire die. The stored heat in the stones and earth kept the chamber comfortable all night. He slept under a single blanket, completely comfortable. In the morning, the interior temperature had dropped to perhaps 58 degrees. He lit another small fire, warmed it back up, and went about his day. The contrast with his previous winter was staggering. The winter before, in his log cabin, he'd burned approximately 4 cords of wood per month. That's roughly 500 cubic feet of wood, requiring hundreds of hours of cutting, splitting, and hauling. In his earth shelter, he burned less than 1 cord per month, and he was warmer, more comfortable, and infinitely less exhausted. When other trappers visited Jacob that winter, they couldn't believe what they saw. The entrance, half buried in snow, looked like nothing more than a den or a cave. But inside it was warm, dry, and comfortable. The walls were smooth earth, hung with shelves and pegs for storage. The floor was clean and dry. A small fire flickered in the stone firebox. The air was fresh, not smoky. The space felt secure, protected, almost womb-like. "You're living like a badger," one trapper said, but there was no mockery in his voice. Only amazement. Jacob just smiled. "The badger knows something we forgot," he replied. The efficiency of Jacob's earth shelter came from multiple principles working together. First was thermal mass. The earth surrounding the shelter, Tons and tons of soil acted as a massive heat sink. During any period when the interior was warmed, whether from a fire, from body heat, or from solar gain through the entrance, that heat would slowly transfer into the earth walls. The earth would absorb it and store it. Then, when the interior temperature dropped, the earth would release that heat back, slowly and steadily. This thermal flywheel effect meant temperature swings inside the shelter were minimal. While the outside air temperature might vary by 60 or 70 degrees between day and night, the interior temperature might vary by only 5 or 10 degrees. Second was insulation. The 3 feet of earth covering the roof provided excellent insulation, with an R value far superior to any practical thickness of wood. Earth is actually a decent insulator, especially when dry, and the depth of earth meant that heat had a long, slow path to travel before reaching the cold air above. Heat transfer is a function of temperature difference, surface area, and distance. By increasing the distance, Jacob dramatically reduced the rate of heat loss. Third was protection from wind. Wind is one of the biggest heat thieves in cold climates. It strips away the boundary layer of warm air around any surface, constantly replacing it with fresh cold air and accelerating heat loss. This is the wind chill effect. Underground, there is no wind. The air is still. This means that any heat in the structure stays in the structure. The only way for heat to leave is through slow conduction through the earth, which takes hours or days rather than seconds or minutes. Fourth was ground coupling. By building into the earth rather than on top of it, Jacob was coupling his living space to the stable temperature of the earth itself. The earth at depth doesn't freeze. It stays at that 55-degree temperature year-round. His floor, his walls, his ceiling were all in direct contact with this thermal reservoir. This meant his baseline temperature, the temperature his space would settle at with no added heat, was 55 degrees rather than the ambient air temperature of -40. That's a 95-degree advantage before he even lit a fire. The engineering principles that made Jacob's shelter work were sophisticated, even if he wouldn't have described them in modern scientific terms. He understood thermal conductivity, the rate at which heat moves through materials. He knew that Earth conducts heat slowly, which makes it a good insulator when you're trying to keep heat in. But he also knew that Earth stores heat well, which makes it a good thermal mass when you want to capture and hold warmth. He understood the stack effect, the principle that hot air rises. By positioning his entrance tunnel lower than the main chamber, and by including the exhaust vent at the highest point, he created a natural circulation pattern that moved stale air out while bringing fresh air in. He understood thermal inertia, the tendency of massive objects to resist temperature change. The tons of earth surrounding his shelter had enormous thermal inertia. Once warmed, they would stay warm for a long time. Once cooled, they would stay cool for a long time. This inertia smoothed out the temperature extremes and created a stable environment. He also understood humidity control, though he might not have called it that. The earth walls naturally regulated humidity. When the air became too dry from heating, the earth would release moisture. When the air became too humid from cooking or respiration, the earth would absorb moisture. This created a comfortable, healthy environment without the excessive dryness that plagues modern heated homes, or the excessive dampness that plagues poorly ventilated spaces. Word of Jacob's earth shelter spread through the mountain man community quickly. By the spring of 1837, several trappers had visited to see it for themselves. Some were convinced and began planning their own underground shelters. Others remained skeptical, unwilling to put in the enormous effort required to dig into a hillside when a log cabin could be built in a few weeks. But those who did commit to building earth shelters discovered the same benefits Jacob had found. A trapper named Marcus Boone built an earth shelter in the Bitterroot Range in 1838. His design was similar to Jacob's, but included some innovations of his own. Marcus built his shelter with a second chamber, creating an L-shaped layout. The first chamber served as an entrance, storage, and cold trap. The second chamber, deeper into the earth, was the living space. This design pushed the living area even further from the exterior, providing additional insulation and stability. Another trapper, Samuel Running Deer, a man of mixed Lakota and French heritage, built what he called a winter lodge that combined earth sheltering with native building techniques. His structure was built into the side of a ravine, with the roof covered not just with earth but with a layer of sod thick enough that grass and small plants grew on it. The living roof provided extra insulation and also made the structure nearly invisible from a distance. This was valuable protection against hostile groups who might target an isolated trapper. A settler named Hans Eriksson, who'd immigrated from Sweden, built a variation that incorporated his knowledge of Scandinavian building. He lined the interior walls of his earth shelter with vertical logs, creating a wood-paneled interior that felt more like a conventional cabin. The logs were spaced a few inches from the earth walls, creating an air gap that provided additional insulation and also kept moisture from the earth away from the wood, preventing rot. The air gap became a common refinement. Builders discovered that earth walls, while excellent thermal mass, could sometimes transfer moisture to stored goods or create a damp feeling. By adding an interior liner of wood, bark, or even woven mats with an air gap between the liner and the earth, they could maintain the thermal benefits while creating a drier, more comfortable interior atmosphere. The construction techniques continued to evolve through trial and error. Builders learned that the angle of the roof mattered. A flat roof could create drainage problems if not properly sealed. A slightly peaked roof, even underground, would encourage any moisture that did penetrate to run to the edges rather than dripping in the center. They learned that the entrance orientation mattered beyond just solar exposure. An entrance that faced the prevailing winter winds would allow cold air to funnel in with every opening of the door. An entrance positioned perpendicular to the prevailing winds would create a much more stable thermal environment. They learned that the depth of burial mattered. A shelter with only 1 foot of earth covering was still subject to freezing from above. 2 feet was better. 3 feet was ideal for most climates. Beyond 3 feet, the added benefit was minimal unless you were in an extremely cold location. They learned about the importance of drainage. An earth shelter dug into a hillside needs careful attention to water management. Runoff from rain or snowmelt above the shelter must be diverted around it, not allowed to flow through it. This usually meant digging a shallow trench above and to the sides of the shelter to intercept and redirect water. Inside the shelter, any moisture that did seep through the walls or enter through the ventilation system needed a way out. This is why most successful designs included a sump pit, a small hole dug at the lowest point of the floor where water could collect and either evaporate or be bailed out periodically. The psychological aspects of living underground were something that had to be managed. Some men found the earth shelter claustrophobic at first, especially those accustomed to the open spaces of the mountains. The lack of windows, the enclosure by earth, the muffled quality of sounds, all created a sensory environment very different from a surface cabin. But most adapted quickly. They found that the security and comfort outweighed the unfamiliarity. The complete silence underground was actually soothing after the constant wind noise of surface living. The stable temperature was a profound luxury after the temperature swings of a conventional cabin. The darkness was easily solved with candles or oil lamps, and many men commented that the soft lamplight in an earth shelter was more pleasant than the harsh light in a drafty cabin. Some builders added clever touches to make the space feel more open. A small window near the entrance, even if it didn't provide much light, gave a psychological connection to the outside world. A higher ceiling in the main chamber, 9 or 10 feet instead of 7, created a sense of space. Painting the earth walls with a mixture of clay and lime created a lighter, more reflective surface that made the space feel brighter. The use of white or light-colored fabrics for wall hangings had the same effect. Jacob's original shelter served him for over 12 years. He finally abandoned it in 1848 when he left the trapping life and moved to Oregon Territory. The structure itself remained sound. When he left, he gave a tour to a young trapper who was considering buying his trap lines. They descended into the earth shelter together, and Jacob pointed out each feature, explaining why he'd built it that way. The walls were still solid, showing no signs of collapse or erosion. The floor was still dry. The roof, after 12 winters of snow and rain, showed no leaks. The firebox stones were blackened from years of use but structurally intact. The ventilation pipes still functioned perfectly. The young trapper, whose name was recorded as James Morrow, bought the trap lines and moved into the shelter. He lived there for another 7 years. By 1855, the beaver trade had collapsed completely, and Morrow moved on. The shelter was abandoned, left to the elements. Over the decades, the entrance partially collapsed. The wooden door rotted away. The ventilation pipes crumbled. But even as late as the 1920s, over 80 years after Jacob built it, trappers and hunters occasionally used the shelter. The main chamber, dug deep into stable earth, remained intact. The roof, supported by its stout posts and heavy beams, still held tons of earth without sagging. It was still dry inside, and it was still noticeably warmer in winter than the outside air. The knowledge of building earth shelters spread beyond the trapping community. Settlers moving into the mountain territories in the 1850s and 60s encountered these structures and recognized their value. Some homesteaders built earth-sheltered root cellars for food storage, recognizing that the stable 55-degree temperature was perfect for keeping vegetables from freezing in winter and spoiling in summer. Others built earth-sheltered workshops or dairies, places where they needed to work in winter but didn't want to burn excessive fuel. A few built earth-sheltered homes, usually in combination with conventional above-ground structures. A common design was to build a conventional cabin for summer use and an earth-sheltered structure for winter living. This gave the best of both worlds, light and airiness in summer, warmth and security in winter. The engineering principles understood by Jacob and his contemporaries were rediscovered, or perhaps discovered independently, by multiple cultures throughout history. The Inuit people built semi-subterranean winter houses, with the living space partially below ground level and insulated with earth and sod. Ancient peoples in cold climates, from Iceland to Siberia, built turf houses with thick earth walls and roofs. American pioneers on the Great Plains built soddies, houses made from bricks of prairie sod, which functioned on similar principles. In every case, the builders understood the same fundamental truth. The earth is a thermal reservoir, and by building into it rather than on top of it, you can tap into that thermal stability. Before we continue with more details about how these underground shelters evolved, I want to remind you to hit that subscribe button if you haven't already. We're uncovering forgotten knowledge that could literally save your life, and there's much more to come. Modern earth-sheltered building, which emerged in the 1970s during the energy crisis, is essentially a rediscovery of principles that mountain men understood in the 1830s. Contemporary earth-sheltered homes use modern materials, poured concrete instead of logs, synthetic waterproofing instead of clay, mechanical ventilation instead of natural draft. But the core principles are identical: thermal mass, insulation, ground coupling, wind protection. The difference is that modern builders have precise calculations, computer modeling, and engineered materials. The mountain men had observation, experience, and intuition. Both approaches work because they're based on the same physics. Some modern survivalists and homesteaders are returning to these traditional techniques, building earth-sheltered structures with hand tools and local materials. They're discovering what Jacob knew, that with patience, hard work, and understanding of basic principles, it's possible to create a comfortable shelter that requires minimal external energy input. The environmental benefits of earth-sheltered building are substantial. Reduced heating and cooling requirements mean reduced energy consumption. Using local materials means reduced transportation costs and emissions. Building into the landscape means reduced visual impact. A well-designed earth shelter can be nearly invisible, blending into the natural topography. For modern preppers and survivalists, earth-sheltered structures offer specific advantages. They're difficult to detect from a distance. They provide natural protection against wind, fire, and extreme weather. They maintain stable temperatures without external power. They can be built with minimal purchased materials if land and labor are available. They provide excellent security, with earth walls that can't be easily breached. But they also require specific conditions and significant effort. You need suitable soil, clay or clay loam that will compact well and hold its shape. Sandy soil won't work. Rocky soil is difficult to excavate. You need good drainage, a hillside location with natural slope away from the structure. Building in a low area that might flood is asking for disaster. You need time, excavating and building an earth. Shelter is measured in months, not weeks. You need understanding. Mistakes in waterproofing or ventilation can create serious problems. The decline of earth-sheltered building knowledge corresponds with several historical trends. The expansion of the railroad made lumber cheap and readily available in areas where it had been scarce. This reduced the economic advantage of earth shelters compared to wood frame buildings. The development of effective heating systems, first wood stoves, then coal, then oil and gas, made it possible to heat poorly insulated buildings cheaply. This reduced the thermal advantage of earth shelters. The cultural association of earth-sheltered living with poverty or primitiveness made it socially undesirable. As communities developed and social status became important, people wanted homes that looked prosperous, and earth shelters looked like desperation. The lack of building codes and professional standards meant that poorly built earth shelters would fail, collapse, or flood, giving the entire concept a bad reputation. A well-built earth shelter like Jacob's would last for generations. A poorly built one might collapse in the first heavy rain. Most people only heard about the failures. The transition from a frontier survival mindset to a settled society mindset changed priorities. On the frontier, the priority was survival with minimal resources. Efficiency and functionality mattered more than appearance or convention. In settled society, appearance, conformity, and social signaling became important. An earth shelter might be more efficient, but a conventional house looked more respectable. So the knowledge faded. By the early 20th century, very few people knew how to build an effective earth shelter. The skills and understanding were forgotten, relegated to history books and ethnographic studies. But the physics hasn't changed. The Earth still maintains a stable temperature year-round. Thermal mass still stores and releases heat. Insulation still slows heat transfer. The principles that made Jacob's shelter work in 1836 would make an earth shelter work today. What we've lost isn't the laws of thermodynamics. We've lost the accumulated practical knowledge of how to apply those laws with simple materials and hand tools. We've lost the willingness to do hard physical work for long-term benefit. We've lost the understanding that the earth itself can be a building material and a heating system. The mountain men who built earth shelters weren't primitive or backwards. They were practical engineers solving real problems with available resources. They observed, they experimented, they learned from failures, and they shared successful techniques. The shelters they built were sophisticated structures that demonstrate deep understanding of heat transfer, structural engineering, and climate adaptation. Jacob Whitmore's earth shelter, built in 1836, kept him comfortable through 12 rocky mountain winters. It required minimal fuel, minimal maintenance, and minimal cost after the initial construction. It was quiet, secure, and stable. It represented a level of energy efficiency that most modern homes can't match. The shelter stood for over 80 years with minimal degradation. The principles it embodied are still valid, and the knowledge of how to build such structures is worth preserving. Today, when we talk about sustainable building, energy efficiency, and climate adaptation, we're often reinventing solutions that were common knowledge on the frontier. We talk about passive solar design. The mountain men oriented their entrances to catch winter sun. We talk about thermal mass. They built with stone and earth. We talk about super insulation. They buried their structures under 3 feet of earth. We talk about air source heat recovery. They pre-warmed incoming air by running it through earth pipes. Every principle we consider innovative was understood and applied by men with hand tools and practical experience. The difference is scale and complexity. Modern earth-sheltered buildings are larger, more complex, more refined. But the fundamental approach, building into the earth to access its thermal stability, is exactly what Jacob Whitmore did in 1836. The story of how mountain men engineered underground heat traps is a story about observation, adaptation, and the willingness to challenge conventional wisdom. Every other trapper was building log cabins because that's what everyone did. Jacob built an earth shelter because he understood it would work better. He was willing to invest enormous effort in something that looked strange to his peers because he understood the long-term payoff. The mockery he initially faced turned to respect when other trappers saw him comfortable and warm while they shivered and burned through firewood. This is a pattern we see repeatedly in frontier history. The innovators who broke from convention often faced skepticism or ridicule until their methods proved superior. Then everyone wanted to learn the new technique. The knowledge of earth-sheltered building deserves to be preserved and taught. Not because we should all abandon modern construction and move into hillsides, but because the principles involved teach us about fundamental relationships between humans, shelter, and environment. Understanding thermal mass teaches us about energy storage. Understanding ground coupling teaches us about accessing renewable geothermal energy. Understanding natural ventilation teaches us about air quality without mechanical systems. Understanding the work required to build an earth shelter teaches us about the relationship between effort and reward, between short-term convenience and long-term benefit. These are lessons that remain relevant regardless of the specific type of shelter we choose to build. The mountain men who built earth shelters also teach us about resilience and self-reliance. They didn't wait for someone to solve their problems. They observed, they thought, they experimented, and they built solutions with their own hands. They took responsibility for their own survival and comfort. They were willing to work hard today to make life easier tomorrow. These are attitudes that seem increasingly rare in a world where we expect solutions to be provided by others, where we value convenience over capability, where we choose comfort today even if it creates problems tomorrow. The contrast between Jacob's approach and modern approaches is instructive. Jacob spent 6 weeks of hard labor digging into a hillside. That effort bought him 12 years of comfortable winters with minimal fuel consumption. Most modern people wouldn't even consider such a trade-off. 6 weeks of brutal physical labor? For what? We'd rather buy a house, install a heating system, and pay the monthly utility bill. We've chosen to pay with ongoing money and dependency rather than with upfront effort and independence. Neither choice is inherently wrong, but it's worth understanding what we've traded away. The environmental footprint of Jacob's shelter was essentially zero. He dug earth with hand tools, cut logs with a handsaw, and built with materials he found within walking distance. The structure provided decades of service without requiring external energy input beyond small amounts of firewood. When it was abandoned, it simply became part of the landscape again. A modern house requires massive energy inputs for construction, material transport, and manufacturing. It requires ongoing energy for heating, cooling, and maintenance. When it's demolished, it generates tons of waste material that must be transported to landfills. The modern house provides more space, more convenience, more comfort in some ways, but the resource cost is orders of magnitude higher. Again, neither approach is inherently superior for all purposes. but understanding the trade-offs helps us make informed decisions. The story of underground heat traps also connects to broader questions about progress and technology. We tend to assume that newer is better, that modern methods are superior to historical ones. Sometimes this is true. Modern medicine is vastly superior to frontier medicine. Modern communication is vastly superior to frontier communication. But modern heating isn't necessarily superior to earth-coupled passive solar heating. It's more convenient, certainly. It's more flexible. But it's not more efficient in terms of energy input versus thermal output. A well-designed earth shelter can maintain comfortable temperatures with almost no energy input. A modern house, even a well-insulated one, requires substantial energy input for heating and cooling. The modern house provides other benefits that might outweigh the energy cost, but in pure thermal efficiency, the earth shelter wins. This suggests that progress isn't always linear, that newer technologies don't always represent improvement in every dimension. Sometimes old methods are actually superior for specific purposes. The key is understanding the strengths and limitations of each approach and choosing appropriately. For someone interested in building an earth shelter today, the process would be similar to Jacob's approach, but with some modern refinements. Site selection remains critical. You need well-drained soil, stable geology, and appropriate slope. A geotechnical assessment would be valuable. Excavation can be done with modern equipment if available, dramatically reducing the time required. A backhoe can do in hours what took Jacob weeks with a shovel, but hand tools still work if necessary. As structural support can use modern materials, steel I-beams instead of log posts, pressure-treated lumber instead of raw logs. But the basic principle of supporting the earth load remains the same. Waterproofing can use modern membranes. Rubber roofing, plastic sheets, spray-on waterproofing. These provide more reliable moisture protection than clay alone. But traditional methods still work if applied carefully. Insulation can be enhanced with modern materials. Rigid foam board on the exterior of the structure, fiberglass bats on interior walls. But earth itself provides significant insulation value. Ventilation can be mechanized with fans and filters, or kept simple with natural draft pipes as Jacob used. Modern building codes in most jurisdictions would require specific features, proper engineering calculations for structural support, approved waterproofing systems, mechanical ventilation meeting air quality standards, permitted electrical and plumbing systems. These requirements add complexity and cost, but also increase safety and reliability. The fundamental concept remains valid. A structure built into the earth will maintain more stable temperatures and require less heating and cooling energy than a structure built on the surface. Whether you use hand tools and natural materials or modern equipment and engineered systems, the physics works the same way. The legacy of mountain man earth shelters extends beyond the specific structures. It includes the knowledge that alternative building methods are possible, that convention isn't always optimal, that working with nature can be more effective than fighting against it. These lessons apply to more than just building. They apply to any situation where we're trying to solve a problem or meet a need. Do we follow convention because it's familiar, or do we think carefully about what would actually work best? Do we choose short-term convenience or long-term benefit? Do we work with the resources and conditions we have, or do we insist on forcing our predetermined solution regardless of context? The mountain men who built earth shelters demonstrate a different way of thinking about problems. They started with the environment and asked how they could adapt to it. Modern thinking often starts with a desired outcome and asks how we can force the environment to accommodate it. Both approaches have their place, but we've largely forgotten the adaptive approach. We've become so accustomed to technological solutions that we forget to ask whether a simpler, lower-tech approach might work as well or better. Jacob Whitmore died in Oregon Territory in 1871 at the age of 63. By that time, The beaver trade was a distant memory. The frontier had moved west to the Pacific coast, and the mountain men who'd explored and trapped in the Rockies were passing into legend. Jacob had spent his later years farming, occasionally guiding wagon trains through mountain passes and telling stories about his trapping days to anyone who'd listen. His earth shelter in the Wind River Range was rarely mentioned in these stories. It wasn't dramatic. It didn't involve grizzly bears or hostile Indians or blizzard rescues. It was just a hole in a hillside that kept him warm. But to those who understood what he'd accomplished, the shelter was perhaps his greatest achievement. More than any animal he'd trapped, any adventure he'd survived, that simple structure demonstrated genuine understanding of how to live in balance with a harsh environment. The shelter itself has long since returned to the earth. The entrance collapsed decades ago. The roof timbers have rotted. The ventilation pipes have crumbled. All that remains is a slight depression in a hillside, slowly filling with forest debris and growing over with vegetation. There's no marker, no plaque, no recognition that anything significant ever stood there. But the knowledge that shelter represents, the understanding of thermal mass and ground coupling and natural ventilation, that knowledge is being rediscovered. Modern builders studying earth-sheltered construction are learning the same lessons Jacob learned nearly 200 years ago. The earth maintains stable temperatures. Thermal mass stores and releases heat. Natural ventilation can provide fresh air without mechanical systems. Working with the environment is more effective than fighting against it. The mountain men who engineered underground heat traps understood something we're only now beginning to remember, that the most advanced technology isn't always the most appropriate technology. Sometimes the best solution is the simplest solution, the one that works with natural processes rather than requiring constant energy input to override them. An earth shelter that maintains 55 degrees naturally is more sophisticated, in a real sense, than a poorly insulated surface building that requires constant fuel to maintain temperature. The shelter requires understanding and skill to build, but once built, it functions with minimal input. The surface building is easy to build, but requires constant resources to operate. We've confused ease of construction with sophistication of design. We've confused high-tech materials with intelligent solutions. The mountain men knew better. They judged a shelter not by how it looked or how quickly it could be built, but by how well it performed over years of use. By that standard, Jacob Whitmore's earth shelter was a masterpiece. It kept him comfortable through over 100 mountain winters. It required minimal fuel and minimal maintenance. It was built entirely with local materials and hand tools. It demonstrated deep understanding of thermal dynamics and practical engineering. And it proved that with knowledge and effort, a man could create a home that worked with nature rather than against it. That lesson, learned in a hillside in the Wind River Range in 1836, remains as valid today as it was then. The details have changed, the materials have evolved, but the fundamental principle endures. The earth itself is a resource, a thermal battery that we can tap into if we understand how. The mountain men who built underground heat traps knew this, and in knowing it, they survived and thrived in conditions that would defeat most modern people, despite all our technology and resources. That knowledge is worth remembering. It's worth preserving. It's worth passing on to those who come after us, because someday someone might need it. And when that day comes, they'll be grateful that the story was told, that the knowledge was preserved, that the lesson was learned. The earth itself can keep you warm if you know how to ask it.